Many tools support your infrastructure management. Every tool has a data store. Which tool contains the most accurate and complete data? Likewise, every process uses one or more tools during its execution. For DCIM to meet your goal of faster, less costly planning and change management, integration of this data is vital. Integration enables a subject matter expert to see the immediate impact of an action or a decision, plus cascading impacts. The obtained DCIM technology is designed to bring this integration to your planning and change management. Obtained DCIM contains a comprehensive data model for the physical, virtual, and logical items in your infrastructure. This enables Obtain to automatically integrate decisions and actions across the entire web of relationships. Information is processed via web services, from many tools, and from manual input. Our demo of Obtain DCIM will start with a look at this data model in action. Our data center has equipment arranged in rows of racks, with power units supplying each row. Here we see that PDU 12-2 supplies power to a set of equipment. PDU 11-1 will be used in this demo. It supplies power to only a few items and will keep the demo simple and focused. PDU 11-1 receives power from two sources, with 50% of the load coming from each source. The obtained data model is able to record every switch point in the power hierarchy. So if this switch point was configured to have all of the power come from a single source and fail over to a second source, Obtain is able to document and understand the implication of this design decision. PDU 11-1 supplies power to external equipment, either through additional power frames or internal power panels and breakers. Each power circuit and every power item on a circuit can be modeled and documented. Currently, the only application supported by this PDU is the production version of a manufacturing application. To show the power of automatic integration, we will make a small change to another application and see the change ripple through the data model all the way over to PDU 11-1. Mission-critical applications run in multiple modes: production, development, quality assurance, etc. Each mode of the application has its own web of supporting equipment, power, software, and network capability. Obtain DCIM is able to model an application, each of the modes it operates in, and the resources used by each mode. In our example, the quality assurance mode of the accounts payable application uses a different set of resources than the production mode of the same application. What happens if someone modifies the application to support a new product or increased capacity? One or more modes of the application may require the use of additional supporting resources. Your infrastructure team will be tasked to plan, communicate, and execute this change. This is where the cost and complication arise. Subject matter experts make decisions. Who should they inform? How much communication is optimum? How do they package the communication? Where do they find the time to make such a package? Obtain DCIM is able to record changes to the resources used by an application. Normally, the changes would be recorded by automatic web service communication from other tools. In this demo, we'll make the change manually, so you can see the ripple effect through the database. VM 128 becomes a supporting resource for the quality assurance mode of the accounts payable application. But where is VM 128 and what infrastructure supports it? We can jump through the database and see VM 128 currently operates inside a Blade Center device. and more specifically, inside blade in slot number 2. Where does this blade get its electrical power from? The answer is PDU 11-1. If we look again at PDU 11-1, we will see that it is now recognized as a supporting resource for the quality assurance mode of the accounts payable application. VM128 operates inside a blade center. It too is recognized as a supporting resource. The blade center resides inside a rack 1-H91, and it also is recognized as a supporting resource. Every infrastructure item, including circuit breakers, power strips, edge switches, cables, etc., is recognized as a supporting resource. Automatic integration. Integration is a vital property of a true DCIM database. So too are dynamically created DCIM views. Here is a high-level view of the entire fiber cable connectivity for this data center. At this level, we see connectivity between logical groupings, such as groups of servers, patch panels, storage, etc. If we select one path from this high-level view and drill down, we see the complete connectivity represented by the path. It consists of a mixture of patch cables and trunk cables. If we select a single fiber pair from inside the trunk cable, a true DCIM database will dynamically generate a view of the full connectivity and impact of the fiber pair. The generated view shows fiber pair 21 as being part of a 108-foot cable, with connectivity on one side through a mounting bracket and harness cable to port 170 of a server. The other side of the fiber pair is connected to port 14 on the back side of a patch panel located at floor tile 38M. The front side of the patch panel has a 12-foot patch cable, which patches over to another panel and onward to port 15 of a switch. The zoning of the switch defines 3 outbound ports. One of the paths leads to port 3-ABLE0 of storage device 0039. During troubleshooting or planning, a person may need to know more about device 39. In a true DCIM database, we should be able to click on the device and jump to a new diagram, dynamically generated to show the complete impact of that device. When obtained DCIM jumps to another view, it highlights the object jumped from. In this case, it is interface 3-ABLE0. We can highlight the path for 3-ABLE0 to show how it changes as we select different tailoring options. Let's zoom out to see the full view of every physical item involved in the connectivity of storage device 39. If we were troubleshooting a single path, a view with all of this data is not very useful, so we can remove some of the items we are not interested in. A fully integrated DCIM database will be capable of dynamically generating a new view with just the items we want to see on each path. If our task does not involve physical planning, we could generate a purely logical view of the connectivity for storage device 39. Another example of integration between physical and logical data can be seen in one of the ports of this server. The physical name of the port is 141, which is important to someone involved with physical cabling. But another person involved in virtual or logical planning would know the same port by a completely different identifier. Obtain DCIM enables you to tailor the data displayed on your DCIM views. In this case, we will show the logical name of the server ports, or CHIPIDs. Physical port 141 is also known as Logical Subsystem 0, port 9. With so many different views possible, it is important for a DCIM database to provide a way that you can create a name for your popular views and save them either as private or shared views. Previously, we saw how a change to an application impacted a Blade Center device. The Blade Center is mounted in rack 1-H91. We can jump to a view of the rack and note that the power infrastructure has been designed to supply a maximum of 10 kW to the rack. 5.7 kW is currently being used. Rack 1-G91 is allocated 11 kW, with 10.5 in use. This exceeds the 80% threshold defined as an alert level. Power allocation and alert levels for all racks and rows of racks can be defined by the power architect. If we are planning the installation of a new server, there are other metrics we need to consider. If it is a 5U server, we can see that we have 72 places in the data center that are exactly 5U's tall. Other metrics, such as the total number of racks, total U's installed and used, stranded U's without available power, and patching ports available, are important for accurate planning. If we decide to mount our new 5U server in rack 1-G91, it will physically fit, but it will cause the power draw for the whole rack to exceed the design allocation. Obtain DCIM can be tailored to not allow this plan to be completed. We would have to choose another rack, 1-H91, for the mount. Note that mounting the server in rack 1-H91 will cause the power draw to increase to 8.2 kilowatts. This exceeds the 80% warning level for the rack. As part of the focused communication Obtain DCIM provides, a set of alarms can be defined for different situations. If a rack exceeds a power warning level, specific people want to be notified. Other situations, such as lease expiries, may be important to a different set of people. Focused communication during process execution is handled more extensively by Obtain Nexus. To generate DCIM views across physical, virtual, and logical boundaries, the Obtain data model includes everything from cables, devices, and patch panels, to VMs and clusters, network zones, data circuits, and applications. But it also includes process-related information for migrations and initiatives, and service definitions, so you can integrate your workflow definition and monitoring into your DCIM database. Obtain DCIM, a complete and true DCIM database to support your investment.